This lesson is on the difference between an ideal gas and a real gas. So there are some assumptions made in the kinetic molecular theory. A couple of those assumptions, the particles that make up a substance have no volume, and those particles exhibit no attractive forces. And so in order for what we've talked about already to hold true, we have to keep those things in mind. Real gases, as we'll see, do not fit this kind of behavior. All right, so fill that in, ideal gases. So again, a ideal gas, an ideal gas, does not have volume and does not exhibit attractive forces. This is not true of real gases. Real gases do have volume. The particles that make up these real gases do have volume and they do exhibit attractive forces. So it says all gases are affected by their size and attractive forces. Now, number one here is different than what we're going to talk about in just a bit. So these are the conditions at which a real gas behaves less ideally. So it says the effects are greatest at low temperatures and high pressures. So at low temperature and high pressure, a gas behaves less ideally. The opposite's also true. At high temperature and high temperature and low pressure, a gas behaves more ideally. So here's what's going on here. At low temperature, the particles of a substance are moving slowly. And because they're moving slowly, this gives them the opportunity to exhibit their attractive forces towards each other. If they're moving fast, then the particles cannot exhibit much attraction towards each other, and thus the substance would behave more ideally. High pressure implies low volume. So if a gas is under high pressure, usually the particles are closer together. If the particles are closer together, then again, they will have the opportunity to exhibit attractive forces towards one another. Take a look on page 433. See a graph there. It shows behavior of different gases as as pressure increases. We see that's the ratio of pressure and volume to N, R, and T. So we're just looking at the ideal gas law for real gases increases. And so as pressure increases, that ratio becomes more pronounced. Page 434 at the top, 1216. We can see what we mean by low pressure versus high pressure. Again, high pressure, those particles are closer together, able to exhibit attractive forces more towards one another, though on the left it shows low pressure particles in general further apart, but you do have some that are, looks like they're colliding perhaps. All right, so here's the deal. We need to compare the volume of an ideal gas to the volume of a real gas. So because the particles of a real gas occupy space, the volume of a sample of a real gas is going to be greater than the volume of an ideal gas. So think of it this way. Think of the distance between the particles of an ideal and real gas being constant, let's say, at some temperature and pressure. Because the particles of a real gas occupy space, then to be the same distance apart from one another compared to an ideal gas, they're going to have to overall occupy a larger volume. So just know that the volume of a real gas is greater than the volume of an ideal gas. And so we need to apply a mathematical correction for the volume of a real gas. I'm thinking ahead to the ideal gas law. So here's what that looks like. So you can do this one of two ways. I'll start off with volume of an ideal gas is equal to the volume of a real gas minus N, which is number of moles, times some constant B being the correction factor for volume. There's a table in your book on page 435. They're called van der Waals constants. And then we can see there. We'll look at that in just a minute. I want to compare different constants for different gases. All right, the other factor we have to consider is that real gases do exhibit attractive forces. That could be dispersion forces, dipole-dipole forces, hydrogen bonding, anything like that. And so that means because of that, the particles of a real gas, because they exhibit attractive forces, don't travel in straight line paths. So the particles of a real gas kind of zigzag their way. So as let's say we have a particle here, and we have particles here and here and here and here. So what's going to happen is this particle, as it moves, it's going to be attracted to that particle, it's attracted to this particle, it's attracted to this particle, and so it's going to have kind of a zigzag movement across the space that it has inside some container. So this would be for a real gas. An ideal gas, because it exhibits no attractive forces, even if there's particles around it in the vicinity, is just going to travel in a straight line path because it is not attracted to those particles. So how does that affect pressure? Well, if the particles of an ideal gas are moving in straight line paths, that means they are going to collide with the walls of their container more frequently. Or because the particles of a real gas do not travel in straight line paths, they take this kind of zigzag path, there's going to be less collisions. And less collisions then results in less pressure. So the pressure of an ideal gas is greater than the pressure of a real gas. So again, we can look at it one of two ways. We'll go, I'm not sure which way it's shown on your equation sheet. So we did volume ideal last time, so let's do pressure ideal. It's equal to the pressure of the real gas plus all of this stuff. Again, this is given to you on your equation sheet, so you don't need to memorize this, but you do need to know what this means. You do need to know that the pressure of an ideal gas is greater than a real gas. The correction factor for that is right here. N being moles again, A, van der Waals constant for pressure. All right, speaking of van der Waals, if we combine all of this, combine the correction factor for pressure and volume, plug that into the ideal gas law, here's what we get. So there's our pressure. There's our volume. And of course, that is equal to nRT. So be careful with your orders of operation here. That's what causes students sometimes the most difficulty. So we have a sum of these things here and a difference here, and we're going to multiply. So you kind of need to factor that stuff out if you're solving for one of those variables. If you have all numbers, of course, just plug in all those numbers, and then you'll be good to go. All right, go back to that table I was referring to earlier, page 435. And let's look at some of these substances. And let's talk about why they have different van der Waals constants. Start with A, which is the correction factor or van der Waals constant for pressure. So the first three substances listed there are all nonpolar. Helium is not considered, I guess, polar or nonpolar, it's just an atom. But all three of those, hydrogen, helium, nitrogen, exhibit only dispersion forces. And so we see that the value for A is really small for those substances. It does increase between, like, say, hydrogen and nitrogen. Remember that the strength of dispersion forces varies with the size of the electron cloud. So nitrogen has a larger electron cloud than hydrogen, therefore has stronger dispersion forces. Therefore, the correction factor for nitrogen is going to be greater than hydrogen. Notice hydrogen is larger than helium. So even though they have the same mass, actually rather hydrogen has a mass of 2 and helium has a mass of 4. I apologize for that mistake. Hydrogen molecules are actually a little bit bigger than helium atoms. You have 2 atoms bonded together in the hydrogen molecule. It's a longer molecule, larger electron cloud. So the correction factor for hydrogen is greater than helium. We get to nitrogen, or sorry, not nitrogen, we get to ammonia. Ammonia exhibits hydrogen bonding, strongest type of intermolecular force, and so we see the correction factor for ammonia is pretty big, relatively speaking. And then the last two there, carbon dioxide and methane, both exhibit dispersion forces. Those are rather large molecules compared to nitrogen and hydrogen, and therefore we see a larger van der Waals constant for those substances. B, the correction factor for volume, same idea. The larger the particle, the larger the correction factor has to be. And so we see that carbon dioxide and methane, they're made up of the most atoms or the largest atoms. So that's what we want to look at. How many atoms is that molecule made of? The more atoms it's made of, the larger the molecule. I'm talking in size in terms of its volume. Or the larger the atoms in that molecule, the larger the molecule. So even though, carbon dioxide is made up of only 3 total atoms, whereas methane is made up of 5 atoms, oxygen atoms are larger than hydrogen atoms, so the correction factor is pretty similar for those two molecules. All right, so let's go ahead and take a look at an application of the van der Waals equation 1223, the bottom of page 435. Read along with me, please. Calculate the pressure exerted by 1 mole of methane in a 500 milliliter vessel at 25 degrees Celsius, assuming ideal behavior. So just calculate pressure using the ideal gas law, and then assuming non-ideal behavior, where we're going to calculate the pressure using the van der Waals equation. Now let's think about this. You calculate the pressure assuming ideal behavior. How will the pressure of this gas be assuming non-ideal behavior? Well, again, the pressure of a real gas is less than that of an ideal gas. So if you turn the page and take a look at the solution, assuming ideal behavior, we get 48.9 atmospheres. Take a look at the van der Waals equation. So we have pressure plus 1 mole squared times the correction factor for pressure for methane, which is 2.25. The units there are liters squared atmospheres per mole squared, so that everything cancels. Divided by the volume squared, 0.500 liters. Take all of that, multiply by the volume, 0.500 liters, minus correction factor, 1 mole, times 0.0428 liters per mole. That's the B for methane, equals nRT. And so what you want to do is we need to distribute those values. So pressure times V minus NB, whatever that is, we got to get that number. And then all of that other part, N squared A over V squared times whatever you get for V minus NB. And then we'll divide and subtract and whatever we need to do to isolate P. So it shows there we get P plus 9.00 atmospheres equals 24.5 liter atmosphere per 0.457 liters equals 53.6 atmospheres. And so solving for P, we get 44.6. Point being, the pressure of methane, assuming ideal behavior, is greater than the pressure of methane, assuming non-ideal behavior. All right, to give you a chance to practice with this, go to page 442 and go ahead and work on number 93. Actually, not a chance to practice this, but I'm going to give you a chance to practice. Go ahead and answer that question first, and then I'll give you a practice problem to work on. Pause now. So what is the difference between a real gas and an ideal gas? Real gases occupy volume. The actual particles take up space. The particles exhibit attractive forces. Under what conditions are the deviations from ideality most important? So I'm not sure exactly what this is asking for. So under what conditions do gases behave most ideally? Go ahead and pause and answer it that way. The conditions at which a gas behaves most ideally are those in which the attractive forces between the particles are minimized. So attractive forces are minimized when the particles are moving fast, hence at a high temperature. And the attractive forces are minimized when the particles are far apart. That would occur when the pressure is low. So gases behave most ideally at high temperature and low pressure. Go ahead and try this one out. We'll use the same problem as example 1223, but instead of methane, let's use carbon dioxide. So calculate the pressure exerted by 1.00 moles of carbon dioxide in a 500 milliliter container at 25 degrees Celsius, assuming ideal behavior and non-ideal behavior. Go ahead and pause the video and set those up. Here is our setup using ideal gas law, so assuming ideal behavior. So 1 mole of carbon dioxide gas at 25 degrees Celsius in a 500 milliliter container will occupy a pressure of 48.9 atmospheres. How about assuming non-ideal behavior? What is the pressure going to be compared to 48.9? Well, it should be less. It should be quite a bit less, even though carbon dioxide exhibits only dispersion forces. It's a somewhat large molecule, so its dispersion forces are somewhat strong. So here's the setup. Sorry, I left some units out just for space. I was running out of room here, so make sure to include units with all of your values. And so I kind of gave you some numbers here. The 1 squared times 3.59, which is a constant for carbon dioxide, divided by the 0.5 squared is 14.36. I guess I can do 14.4 there is fine. And then the 0.5 minus the 1 times 0.0427, the correction factor B for carbon dioxide, you get 0.457. And then on the right side is equal to about 24.5. Divide both sides by 0.457. Subtract 14.36 and you get 39.3 atmospheres, which is what we predicted. The pressure, assuming non-ideal behavior, will be less than the pressure assuming ideal behavior. All right, that concludes this lesson. Thanks for watching.